How many antelopes do you have? For most of you, probably 0. But were you thinking about the fact that you had 0 antelope? Again, probably not. Just as you weren't quantifying the number of antelope you have, for a long time people understood the idea of numbers and quantifying before they included 0. Even now as children, we learn to count before learning about 0 as a number. Because 0 is not tangible. You can't hold 0 of something. It's our first abstract number. The most basic set of numbers that we learn about, both individually as children and as a society through history, is the set of natural numbers, which we denote with a capital N. The natural numbers are all the positive whole numbers, 1, 2, 3, and so on. Note that curly braces are used to contain numbers in our set. After some time, we include 0 in our collection of numbers. For a long time, both individually and historically, the natural numbers with 0 were enough. For now, let's stick with these numbers, 0, 1, 2, 3, and so on. Now that we have these numbers, what do we do with them? Let's pretend that we are hunting antelope in our ancient society. If we are just hunting by ourselves, the numbers are great to count the number of antelope we get. But what if we're not alone? What if we're hunting with a friend? Now, each one wants to count our own antelope individually, but we also want to know how much we have collectively. Let's look at an example. Suppose that you caught 3 and your partner 2. We want to know how many were caught in total. Previously, we only used numbers to count things. This is the first time we try to combine two numbers. This is where addition is born. We want to know what is 2 plus 3. In other words, 2 plus 3 equals what? This may seem silly and easy now, but at one point it was hard. Counting our first 3, then our next 2, we see that 3 plus 2 equals 5. Let's continue with our example. What if we had counted the 2 first and next added the 3? In other words, 2 plus 3 equals what? Of course, 2 plus 3 is 5, just like 3 plus 2 is 5. It doesn't matter what order we add them in. This is our first property of addition. And there is nothing special about the numbers 2 and 3 here. The commutative property of addition says that for any numbers a and b, a plus b equals b plus a. Let's continue with our hunting example. Again, suppose that you caught 3 antelope, but this time your partner didn't catch any. In other words, your partner caught 0. Here's where having the number 0 comes in handy. So if we want to know how many you caught in total, again what we're trying to figure out is 3 plus 0 equals what? And again, we of course know that 3 plus 0 equals 3. But there's something special here about adding 0. This teaches us our next property of addition. 0 is called the additive identity. For any number a plus 0 equals a, and 0 plus a also equals a. Now, since your friend didn't catch any antelope, you share. You give them one of yours. Now the question becomes, how many are left for you? We want to combine our number 3 with their number 1, but this time not with addition. We need something new. This is where subtraction is born. We want to know 3 minus 1 equals what? Again, this may seem silly and easy now, but at one point it was hard. Starting with our 3 and removing 1, we see that 3 minus 1 equals 2. We're just glad that we didn't need to give them all 3 of ours, because then we would have 0 left. That is, 3 minus 3 is 0. And 3 is not special here. This is true for any number a. A minus a equals 0. Now we have our first property of subtraction. For any number a minus a is 0. Remember our commutative property for addition, a plus b equals b plus a? Does this work for subtraction? Let's pick two numbers and try. What about 5 and 3? 5 minus 3 is 2, but what's 3 minus 5? Well, if we use our numbers 0, 1, 2, 3, and so on, that doesn't even make sense. Clearly, subtraction is not commutative. Since addition is nicer, let's stick with addition for now. Let's continue with our hunting example. As we keep hunting and eating, we learn that our society needs 4 antelope to eat for an entire week. We know that we can consistently catch 3 antelope. How many does our not so consistent hunting partner need? Since we know we add our numbers together, this is addition. But different than what we did before. Now the question we have is 3 plus what equals 4? Like before, we were trying to figure out a number. But now we want to be able to add the number that we don't know. This is where algebra is born. And because question mark is not a very easy symbol to work with, we will call our unknown number x. We now have a name for the number we're looking for, x. But how do we find out what it is? In other words, what number is x? To answer this, we can start picking numbers from our list up there and keep adding our 3 to them. If x is 0, then we caught 3 plus 0, which is 3. That's not enough. Let's try something bigger. If x is 3, then we caught 3 plus 3, which is 6. That's too much. Let's try something smaller. If x is 1, then we caught 3 plus 1, which is 4. That's it. They need 1 antelope. We will call this number that works our solution. Although this technique is inefficient, it works. And never underestimate something that works. And don't worry, we will work on efficiency throughout the course. For now, we are hunter-gatherers, happy that we just figured it out. Now, as we gather more and hunt less, we have time to think. In our time spent not hunting, we think about this algebra. We saw that 0 is important to addition. So we wonder, 3 plus what equals 0? What is the solution? What is the number for x that works? As before, we can try numbers from our list and check. If x equals 2, then we caught 3 plus 2, which is 5. That's too much, so let's try something smaller. If x is 1, then we caught 3 plus 1, which is 4. That's too much also. Let's try something smaller. If x is 0, then we caught 3 plus 0. Does that equal 0? No, that's too much again. We need to try something smaller. But we don't have any numbers smaller. At least not yet. Just like when we started including 0, we need new numbers. In other words, none of the numbers we have so far solve the problem. So we need to make one up. We call our new number that solves our equation -3. Even though we had to make it up, we have a solution. 3 plus -3 is 0. We don't stop at 3 though. Let's keep going. Let's define -1 so that 1 plus -1 is 0. And -2 so that 2 plus -2 is 0. And -100 so that 100 plus -100 is 0. For every number on our list, let's do the same. We define the negative of a number as the number we add to it to get 0. Our new number set is called the integers, and we label it with a capital Z. So now we have a new set of numbers to work with. We invented our new numbers so that for any number a plus -a is 0. We first saw that negative 3 is the number we add to 3 to get 0, and that negative 2 is the number we add to 2 to get 0, and that negative 100 is the number we add to 100 to get 0. But what is the negative of negative 3? Remember, the negative of a number is the number we add to it to get 0. So negative 3 is the number we add to negative 3 to get 0. What number do we add to negative 3 to get 0? We saw negative 3 plus 3 is 0. So since 3 is the number we add to negative 3 to get 0, negative 3 is 3. Again, there's nothing special about 3 here. For any number a, the negative of negative a is just a itself. Let's look back at what we learned so far about our integers. We invented our new numbers so that for any number a plus negative a was 0. But also remember our property for subtraction, that a minus a is 0. These are nearly identical. A plus negative a equals a minus a. And it doesn't matter if we start with a or another number b. In general, b plus negative a is the same as b minus a. So we can replace subtraction with addition of a negative. And we can replace addition of a negative with subtraction. This versatility will be useful. Now that we've spent some time to think, let's get back to hunting. On our next trip, we go in a group of 3. You catch your usual 3, while your 2 partners catch 2 and 4. Again, we want to know how many we caught in total. We want to add the numbers 3 plus 2 plus 4 to see what it is. But with addition, we can only add 2 numbers at a time. So which 2 do we add first? If we add 2 and 3 first, we get 3 plus 2 plus 4, which is 5 plus 4, which is 9. What if we add the 2 and 4 first? Then we have 3 plus 2 plus 4. Well, 2 plus 4 is 6, so we have 3 plus 6, which is 9. It doesn't matter what order we add the 3 numbers. The associative property for addition says that for any numbers a, b, and c, a plus b plus c equals a plus b plus c. In other words, if we're only doing addition, it doesn't matter what order we add them in. So in general, we won't use the parentheses here. Now, let's keep hunting. In our next trip, you catch 3, and your partners each catch 3 also. So in total, you caught 3 plus 3 plus 3. Well, 3 plus 3 is 6, plus another 3 is 9, so we caught 9 in total. But as our society expands, we need more food, so we need 4 hunters, who each catch 3, for a total of 3 plus 3 plus 3 plus 3. To do this, we add the first 2 3s to get 6, then we add the next 3 to that to get 9, and our last 3 to that to get 12. So 3 plus 3 plus 3 plus 3 equals 12. Now let's continue this. But what if we have 5 hunters who each catch 3? Well, then we have 3 plus 3 plus 3 plus 3 plus 3. Adding the first 2 3, we get 6. Adding another 3, we get 9. Another 3 gives us 12. And our last 3 gives us 15. So 3 plus 3 plus 3 plus 3 plus 3 equals 15. But what if we keep growing, and now we have 10 hunters who each catch 3 antelope? Well, we have 3 plus 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 3. What does this give us? Well, this addition problem isn't difficult, but it sure is tedious. We need something more efficient. This is where multiplication is born. Multiplication, a times b, means that we add a to itself b times. So our problem becomes 3 plus 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 3 equals 3 times 10, which is 30. This is a much nicer way to do this problem. Let's spend more time thinking about this multiplication. We can visualize the multiplication in terms of blocks. For example, if we have 4 times 3, by definition, this means 4 plus 4 plus 4 3 times, which we know gives us 12. But we can visualize the multiplication of 4 times 3 as a rectangle of width 4 and height 3. In other words, we have 4 blocks stacked on top of themselves 3 times. In using this visualization, it helps us see that if we compute 3 times 4, we get the same rectangle, just on its side. So we see here that 4 times 3 equals 3 times 4. And there's nothing special about 4 and 3. In general, the commutative property of multiplication says that for any numbers a and b, a times b equals b times a. This is very similar to our commutative property of addition. We have now seen that both addition and multiplication are commutative. That is, a plus b equals b plus a, and a times b equals b times a. Also similar to addition, multiplication is associative. That is, for numbers a, b, and c, if we first multiply a times b and then multiply by c, that's the same as if we first multiply b times c and then multiply by a. So if we are only multiplying, we can multiply in any order. As an example, if we have 2 times x times 5, we can reorder it to be 2 times 5 times x, then multiply 2 times 5 together first, since we know how to do that, to get 10 times x. It's worth noting that moving forward, we may not show all these steps, but they'll be working in the background. We saw one more aspect of addition, which is the identity 0. In particular, we saw that 0 is the additive identity, and that for any number a plus 0 equals 0 plus a. We have something similar for multiplication as well, but this time it's not 0. 1 is the multiplicative identity, which means that for any number a times 1 is the same as 1 times a is just a. We can see that there are a lot of similar properties for both addition and multiplication. Now, let's continue this pattern of understanding multiplication as we did addition. We saw for addition that it gave rise to an opposite operation, which we called subtraction. As an example to see why subtraction is the opposite of addition, if we start with 3 and then add 4 and then subtract 4, we get 3 plus 4 minus 4, which is just back to where we started at 3. And in general, if we start with any number x and then add y and then subtract y, we get x plus y minus y is just x. These two operations undo each other. Similarly, multiplication has an opposite operation. This is called division. For any number x, if we multiply by y, then divide by y, we get x times y divided by y is just x. Throughout the course, we will use these opposite operations to solve equations. Remember with addition, we wanted to know if there was a number we could add to 3 to get 0. We were using the additive identity 0 to create our negative numbers. We want to do something similar now with multiplication. Specifically, we may want to know if there are any numbers we can multiply 2 by to get the identity 1. In other words, can we solve the equation 2x equals 1. Well, that means we need a number so that 2 of it gives a total of 1. But we run into the same problem we had before with negative numbers. We can't solve this equation with any of the numbers we have so far, because we only have the integers. So again, we need new numbers. The number we need, we call 1/2. 1/2 is defined as the number so that 2 times 1/2 equals 1. Similarly, we can define 1/3 as the number so that 3 times 1/3 equals 1. And in general, 1 over n, or 1/n, is the number so that n times 1/n equals 1. But now that we have these new numbers like 1/2 and 1/3, we need to look at how to combine them with addition and multiplication, as well as subtraction and division. For now, let's focus on addition. For example, how do we combine 1/3 plus 1/3? Looking at it just from a language point of view, if we have 1 dog plus 1 dog, we have 2 dogs. And if we have 1 pen plus 1 pen, we have 2 pens. So if we have 1/3 plus 1/3, we have 2/3. And we write the number 2/3 as 2 over 3. Doing this, we get a whole new group of numbers of the form m over n, where m and n are integers. We call these the rational numbers, and we represent them with a q. In particular, we write q as the set of numbers m over n so that m and n are integers, and we need to make sure that n is not 0. And while there are a lot of rational numbers, in fact there's infinitely many, there are still some numbers that are not fractions. Famous examples include pi and the square root of 2. In fact, between any two fractions, no matter how close together there is a number which is not a fraction between them. We call this set of all numbers between any two fractions the real numbers, which we sometimes shorten to just r. Because there are no gaps between real numbers, just more real numbers, we represent the numbers with a continuous line. We will refer to this as the real number line. This will be our biggest set of numbers for now, but later in the semester we will add to it one more time. So we have now seen some of the classical number sets. We started with the natural numbers, then added 0 and the negatives to get what we call the integers. Division led us to looking at fractions, and finally we had the number line, which we call the real numbers. But there are other sets too, such as the even numbers, which we would write as 2n so that n is an integer. For example, we could have the set of numbers -1, 3, and 4, or we could have the set of numbers 0, pi, and 10. We can see from our classical sets and our examples that sets of numbers can either be infinite or finite. We have now seen the 4 basic operations to combine numbers. First, we had addition. For example, 3 plus 4 equals 7. We saw the commutative property, which said for a and b, a plus b equals b plus a. We have the associative property for addition, that for numbers a, b, and c, a plus b plus c equals a plus b plus c. We also had the additive identity, which said for any number a plus 0 equals 0 plus a is just a. And with addition came its opposite, subtraction. For example, 7 minus 4 equals 3. And we can understand subtraction as addition of negatives. So our example 7 minus 4 we can rewrite as 7 plus -4, which is 3. This allows us to use all the properties that we have for addition, which we don't have for subtraction. After learning addition and subtraction, we next learn multiplication. For example, 4 times 3 equals 12. We saw also for multiplication that it has the commutative property. For any numbers a and b, a times b equals b times a. And multiplication also has the associative property. That is, for numbers a, b, and c, if we first multiply a times b and then multiply by c, it gives us the same thing as if we first multiply b times c and then multiply by a. And finally, we saw that multiplication has an additive identity also, which is the number 1. So for any number a times 1 equals 1 times a is just a. And like the pair of addition and subtraction, multiplication has an opposite, which is division. For example, 12 divided by 4 is 3. And we can understand division as multiplication by a reciprocal. For example, we can write 12 divided by 4 as 12 times 1/4, which is 3. And in general, we can change division into multiplication by the reciprocal, which allows us to use all the properties of multiplication which we don't have for division. As a final example, if we do 24 divided by 3/5, we can rewrite this as 24 times 5/3, which if we do the arithmetic is 40.